All right, so this is behavioral analysis problem 8 for the playlist that's on YouTube. And this problem is taken from Cummings' Real Analysis Long Form Mathematics textbook. And so now I'm going to go into problems involving sequences. And this example is taken from Cummings' textbooks, chapter 3, exercise number 2. So we're going to prove the following using the definition of convergence of a sequence. So we have parts A, B, and C. And to show this as far as the definition, I'm going to use the definition for the limit of a sequence or convergence of a sequence based on the YouTube playlist that I made. And so the definition is some sequence AN converges to A as n goes to infinity if and only if for any epsilon bigger than 0 there exists a capital N in the natural numbers such that for all little n bigger than capital N the absolute value of an minus a is less than epsilon. So essentially capital N is the index for the term in which all the terms that come after it are within an epsilon distance of the value that is the value that the limit converges to for that sequence. And a lot of these, it's going to always involve me invoking the Archimedean principle. In fact, in some of these, it's become such common knowledge is that you don't even necessarily need to reference it. But I will for these proofs. But Archimedean principle just says for any real number R, there exists some natural number where the natural number is bigger than R. So based on that, we can find these capital N, and it's going to be dependent on our epsilon value. All right, so I guess I'll go ahead and state that. So we use Archimedean principle to find our cutoff point or index. Cutoff index capital N. That will depend on epsilon. That will depend on E. Okay, so that's how we're going to do these. And I'll first go through a thought process to find that index capital N. So part A is we're going to have the sequence AN equals 7 minus 1 over the square root of N. And then we're going to show this sequence converges to 7 as n goes to infinity. All right, that's what we wish to show. So to do that, I'll first come up with the value for n. So this will be the strategy for finding the necessary capital N. And then I'll do the proof. So basically we need to find some capital N such that for all little n bigger than capital N, we have the absolute value of an minus, in this case, our a is 7, minus 7 is less than epsilon. That's what we're going to do. And we're going to employ the Archimedean principle. So our sequence is 7 minus 1 over square root of n. So I'm going to sort of work backwards with 7 minus 1 over square root of n with what we need to show. So I'll work with this to find the necessary capital N. All right, so 7 minus square root of n minus 7, that just gives us the absolute value of 1 minus or negative 1 over the square root of n. And since this is absolute value, that's going to be less than or equal to just 1 over square root of n. And we need this to be less than epsilon. So note that if n is bigger than capital N, then we have 1 over little n is less than 1 over capital N. And then square rooting both sides, that would also imply that, so this would be like, this implies that 1 over square root of n, little n, is less than 1 over the square root of capital N. And so we need this to be less than epsilon. So working with 1 over the square root of capital N to be less than epsilon. So we're going to rewrite it so that we have capital N. And so what we can do is we can square both sides. And so this is true if and only if 1 over capital N is less than epsilon squared. It's by squaring both sides. And then this is true if and only if capital N is, so taking the reciprocal of both sides reverses the inequality, so that's if and only if capital N is bigger than 1 over epsilon squared. And so we're going to use Archimedean principle to establish this capital N. Okay, and this is all the scratch work. So again, I use the definition of convergence, and basically I'm using all of this. This is just scratch work to find the necessary value for the cutoff index capital N, such that our sequence is within epsilon distance of 7, since 7 is the value that we're proving that it converges to. And so I just worked backwards with 7 minus 1 over square root of n minus 7 as the absolute value of that. It needs to be less than epsilon. Well, that absolute value is equivalent to absolute value of negative 1 over square root of n, and that's less than or equal to 1 over the square root of n, and that needs to be less than epsilon. And we need it so that little n is bigger than capital N. Well, if little n is bigger than capital N, then that means 1 over little n is less than 1 over capital N by taking the reciprocal of both sides. And then if we take the square root, then that means 1 over the square root of little n is going to be less than 1 over the square root of capital N. And then we need 1 over square root of capital N to be less than epsilon. And so that's true if and only if 1 over capital N is less than epsilon squared. And that's true if and only if capital N is bigger than 1 over epsilon squared. And so we can find this capital N by Archimedean principle. All right, so now the actual proof. Again, our sequence is an equal to 7 minus 1 over square root of n. We're showing that converges to 7. So proof, so you're going to be given any epsilon. Given epsilon, we can find by Archimedean principle. By Archimedean principle, we can find an n capital N the natural numbers so that capital N is bigger than 1 over epsilon squared. And And that's because of, again, the Archimedean Principle, which says for any real number, there exists a natural number bigger than that real number. And so our real number in this case is 1 over epsilon squared. And so there exists a natural number, in this case I'm using capital N instead of little n, where capital N is bigger than 1 over epsilon squared. Okay, so we can find that capital N such that that happens. Then for any little n bigger than capital N, we have the following. So the absolute value of our sequence an is 7 minus 1 over square root of n. And then we subtract it from our sequence value is that it converges to is 7, so minus 7. Well, 7 minus 7, those cancel out, so you just have this equivalent to negative 1 over the square root of little n. And that's less than or equal to 1 over the square root of little n. And since n is bigger than capital N, then 1 over square root of little n is less than 1 over the square root of capital N. And then since we know n is bigger than 1 over epsilon squared, then we know essentially this would be like, I guess, in addition to this, since this is true, then we know 1 over n is less than epsilon squared. And since that's true, then the square root of both sides, so 1 over the square root of n, is less than the square root of epsilon squared, which is equal to epsilon. And so we have this last line, 1 over the square root of capital N, is less than epsilon, because our capital N is bigger than 1 over epsilon squared. And that pretty much is the proof. Maybe you could show the yellow stuff if you want. If I wanted to be a little bit extra with it, I could show that. But it's implied since capital N is bigger than 1 over epsilon squared. Okay, so that's that example. The next example. All right, so the part B to the problem says you have a sequence where its nth terms defined to be 2n minus 2 over 3n plus 1, show that this limit is 2/3. Okay, so again, we just need to show for any epsilon, arbitrary epsilon, there exists a capital N, so that for all little n bigger than capital N, we have the absolute value. So it's normally our sequence an minus our value less than epsilon. Our value is 2/3, so an minus 2/3 is less than epsilon. And like before, I'm going to find the capital N that gives us this. So this, again, this is the strategy. This isn't the proof. This is sort of scratch work. So this is the strategy for finding the necessary index value capital N. Again, you usually work backwards with the absolute value of our sequence of an minus 2/3 less than epsilon. And then our sequence is 2n minus 2 over 3n plus 1. So that's going to be the absolute value. 2n minus 2 over 3n plus 1 minus 2/3. And we need this to be less than epsilon. All right, so I'm going to work with this stuff in the absolute value and try to simplify it down. So if I want this to be, same fraction, a single fraction, I can multiply the first one. So the common denominator is going to be 3 times 3n plus 1. So I'd multiply the first one, top and bottom, by 3. Multiply the second fraction, top and bottom, by 3n plus 1. All right, so again, all of this is in our absolute value. So what is this going to be? So you distribute the 3, that makes that 6n minus 6. Distribute the minus 2, so that makes that negative 6n minus 2. And all of that's divided by our common denominator of 3 times 3n plus 1. All right, so we have 6n and minus 6n cancel out. Then we have minus 6 and minus 2 makes minus 8. So this would be less than or equal to 8 over 3 times 3n plus 1. And again, we need all of this needs to be less than epsilon. Okay, so since 3 times 3n plus 1 is bigger than just 3n plus 1, because it's natural number, so this quantity multiplying 3n plus 1 by 3 is going to be bigger than that 3n plus 1. So if we take the reciprocal of both sides, then that tells us 1 over 3 times 3n plus 1 is less than 1 over 3n plus 1. And so 8 over 3 times 3n plus 1 is less than 8 over just 3n plus 1. Just trying to make it a little bit easier to find the necessary capital N. And so we know little n is going to be bigger than capital N. So then this 8 over 3n plus 1 is going to be less than 8 over 3 times capital N plus 1. Okay, so and we need that to be less than epsilon. We need 8 over 3 capital N plus 1 to be less than epsilon. Well, to make itself easier, again, let's see. So 3n plus 1 is bigger than just 3n. So 1 over 3n plus 1 is less than 1 over 3n. So then 8 over 3n plus 1, that's going to be less than 8 over 3n. Since you have a dividing by a smaller number, the quantity is going to be bigger than if you're dividing by a bigger number on the bottom. So really, I simplify it even more. Instead of saying 8 over 3n plus 1 to be less than epsilon, you really just need 8 over 3n to be less than epsilon. Okay, so let me erase this. Again, this is all scratch work. So when is that true? So then I can multiply both sides by 3 over 8. And if I do that, I have 1 over capital N less than 3 epsilon over 8. So I just multiply both sides by 3 over 8. Then taking the reciprocal of both sides, N is going to be greater than 8 over 3 epsilon. Okay, so this is the n that we need. All right, and we're going to use Archimedean Principle. Now, this is just an example of an n. We just need to find an n that makes it work. There could be more than just this particular n. And this particular n is going to be greater than 8 over 3 epsilon. All right, so that way I got 8 over 3n. That's equal 8 over 3 times 1 over capital N. Well, 1 over capital N is less than 3 epsilon over 8. So then I could say this is less than 8/3 times 3 epsilon over 8. So then that all equals epsilon. That's how pretty much is how the proof's going to be done. But now I'm just going to make it more formal. Okay, so now the actual proof. And hopefully this logic makes sense. So I said since 3 times 3n plus 1 is greater than 3n plus 1, the reciprocal of both sides results into 1 over 3 times 3n plus 1 less than 1 over 3n plus 1. And that's just to make it a little bit more simple. So then I could go from here to here. Little n is bigger than capital N, so reciprocal, so that means 8 over 3 times little n plus 1 is going to be less than 1 over 3 times capital N plus 1. And then that's going from there to there. And dividing by 3n plus 1, that's a bigger number I'm dividing by than if I were to divide by just 3n. And so that 8 over 3n is going to be a bigger number. So that's where it results into there. And then I used the 8 over 3 times capital N to find the capital N that makes it work. All right. So now the proof. So given epsilon, by Archimedean Principle, we can find capital N it's a natural number. We can find a capital N such that where this capital N is bigger than 8 over 3 epsilon. So this means, in other words, 1 over capital N is less than 3 epsilon over 8. Then for any little n bigger than capital N, and again, our capital N is bigger than 8 over 3 epsilon, we have the following. So our absolute value of our sequence, the sequence was 2n minus 2 over 3n plus 1, minus the limit value, the 2/3. By some algebra, we got this to be equal to the absolute value of negative 8 over 3 times 3n plus 1. All right, so we did some algebra to combine into one fraction, and then simplified the numerator down, simplified into negative 8. And then that itself is less than or equal to just positive 8 over 3 times 3n plus 1. Well, this is less than just 8 over 3n plus 1. And this itself is less than 8 over just 3 times n, or 3 times little n. But little n is bigger than capital N, so then 8 over 3 times little n is less than 8 over 3 times capital N. And then capital N is bigger than are 8 over 3 epsilon. So 1 over capital N is less than 3 epsilon over 8. So it might help to just write this as equaling 8 over 3 over 1 over capital N. Okay, so that is, so it's more obvious to say that this would be less than 8/3 times, and then our 1 over capital N is less than 3 epsilon over 8. And then you have the 8's divide out, the 3's divide out, and that's equal to epsilon. Okay. So that completes the proof. And we just have this string of inequalities. I just broke 8 over 3 times capital N to be 8/3 times 1 over capital N. So it's more obvious that I'm kind of just comparing the 1 over capital N to be less than that. So 8/3 times 1 over capital N is less than 8/3 times 3 epsilon over 8. All right, so that's part B. Now part C. So part C has the sequence for the nth term is given by 7 minus 1 divided by the square root. And in that square root, you have n plus another square root of n, and then plus 13. And we need to show that this converges to 7. And again, we're going to first find the necessary index capital N. So strategy for finding capital N. All right, so we need our sequence an minus 7 to be less than epsilon, where our sequence an is 7 minus 1 over the square root of all that stuff. And then that's going to be minus 7. Well, the 7's, cancel each other out since it's 7 minus 7. And then we have this to be less than or equal to positive 1 over this, all that same stuff. 1 over the square root of n plus square root of n, and then plus 13. Okay, and I need all of this to be less than epsilon. Well, since whenever we have the square root of n plus square root of n plus 13, that's certainly bigger than just the square root of n plus 13, because we have a bigger number that we're taking the square root of when we consider that square root of little n in that square root. So there's a lot of square roots here. So this is bigger than, and let's see, so then square root of n plus 13, that's also bigger than just square root of n, since n plus 13 is bigger than n. So we can take the reciprocal and that reverses these inequality signs. So that we can go from this part to saying that's less than, well, that's just less than 1 over square root of n plus 13. And that itself is less than 1 over square root of n. But then little n is bigger than capital N. So since little n is bigger than capital N, and 1 over little n is less than 1 over capital N, and that's true even when we square root both sides. So 1 over square root of n is less than 1 over the square root of capital N. So then we could say this string of inequalities, and that's less than 1 over capital N. Square root of square root of capital N. And we need all of this to be less than epsilon. And that's where we had the proof in part A. We actually found that N needs to be greater than 1 over epsilon squared. So that way 1 over capital N is less than epsilon squared, which then implies that square rooting both sides, 1 over square root of capital N is less than the square root of epsilon squared, which is epsilon. All right, so that's our necessary N. So this is the N that we're going to use. And again, all of this is scratch work. Now, here's the proof. And mind you, if you notice any mistakes in these examples that I'm doing, feel free to comment. So the proof, we're given epsilon by Archimedean Principle. We can find a natural number, capital N, where capital N is bigger than 1 over epsilon squared. So that implies, so in other words, and this would be kind of, you don't have to put this in the proof, but I think maybe it helps. So this is kind of like an aside. So if N is greater than 1 over epsilon squared, that means 1 over capital N is less than epsilon squared, which means square rooting, we have 1 over square root of capital N is less than the square root of epsilon squared. Well, the square root of epsilon squared is epsilon. All right, and the stuff in yellow is sort of, you can put it in the proof, but I'm trying to just say it's kind of like off to the side, just based on known information, using capital N being greater than 1 over epsilon squared. So then we have for any little n bigger than capital N, we have again, just do it in yellow. So little n bigger than capital N, which is bigger than 1 over epsilon squared. That would imply that 1 over n, little n, less than 1 over capital N, which is less than epsilon squared. And then square rooting everything. That means 1 over the square root of little n is less than 1 over the square root of capital N, which is less than epsilon. So these are all kind of a shitty implication here, but that's how we can justify it all being less than epsilon. And this is stuff, again, that's not necessary to write in the proof, but you can if you want to. So that's why I put it in parentheses and in yellow. So what's in blue is what the actual proof is. So we're given epsilon by Archimedean principle, we can find a capital N where capital N is bigger than 1 over epsilon squared. So then for any little n bigger than capital N, we have the absolute value of our sequence, which is 7 minus 1 over the square root of all that stuff, n plus square root of n plus 13. That's our sequence, and then minus the value that we're saying it converges to is 7. All right, so the 7 subtract out, so then that gives us, negative 1 over the square root of n plus square root of n plus 13. Okay, so that's less than or equal to just positive 1 over all the same stuff. All right, and this itself is less than 1 over just square root of n plus 13. And then, because that's a smaller number, we're taking the square root of, so you're dividing by a smaller number, makes a bigger number. And then same logic, this will be less than 1 over square root of n, or square root of little n. But then little n is bigger than capital N, so 1 over square root of little n is going to be less than 1 over the square root of capital N. And then because capital N is bigger than 1 over epsilon squared, and then reciprocal, taking reciprocal on both sides and square rooting, we get 1 over capital N is less than epsilon, square root of epsilon squared, which is epsilon. So maybe you could write it as this less than the square root of epsilon squared, which is epsilon. All right, so that completes the proof for this one. And that'll be it for this problem.